Hello everyone. So today we continue with alkali metals. Already we have started the topic alkali metals. The same thing we continue with. The alkali metals density and all we have discussed already. Yeah. So alkali metal hydration of ions. Hydration of ions, up to this we have discussed. Next, electronegativity, electropositivity. Electronegativity, electropositivity. Here. Now here electronegativity of alkali metals is very less. Electropositivity of alkali metals is very high. And metallic character of alkali metals is very high. They're highly metallic, highly electropositive, but least electronegative. Alkali metals. Next. So these metals are highly electropositive and thereby possess low values of electronegativities. So they are highly electropositive. Alkali metals are first A group elements here. First A group elements are highly electropositive. Therefore, they have low values of what electronegativities. Less electronegative but highly electropositive. And metallic character and electropositivity increases. So they have low value, means what, high values of metallic character and electropositivity. Both values will increase. Both the properties will increase from lithium to cesium. Which is most metallic? So cesium is most metallic here. Most metallic and most electropositive. So most metallic and most electropositive element. Most electropositive element is what among all? Cesium. Next, electronegativity of alkali metals decreases down the group. Down the group means lithium to cesium, as the trend of numerical values of electronegativity given below on Pauling scale. So on Pauling scale, the value suggests what now here? The electronegativity of lithium is 0.98, but electronegativity of cesium is 0.79. So 0.98, 0.79. So slowly what is happening? The electronegativity value decreasing, slowly decreasing. And rubidium and potassium have what? Near the same electropositive values. They have potassium and rubidium have same electronegativity values. Electronegativity of potassium is equal to rubidium. Okay, and rubidium is having somewhat more value than what? Cesium. And sodium has more electronegativity than potassium. Lithium has more electronegativity than sodium. So anyhow, francium radioactive, leave it. Anyhow, this cesium again, francium, both will be having same, remember. Cesium and francium both have same electronegativities. Potassium, rubidium have same electronegativities. Lithium has more electronegativity than sodium. Next, francium being radioactive, okay, element, and thus the studies on physical properties of this element are limited. Means what? The studies of francium are very less, very limited, because it is unstable element. Francium is unstable element because it is radioactive in nature. Next, specific heat. Specific heat. It decreases from lithium to cesium. So from lithium to cesium decreases means which will be having more specific heat. Lithium has more specific heat. Cesium has less specific heat. Okay, ma. So the specific heat values in calorie per gram. Calorie per gram given here. So lithium, how much specific heat? 0.941 calories per gram. That means if you take 1 gram, if you take 1 gram lithium, 1 gram lithium, if you want to increase the temperature from suppose 25 degrees Celsius to 26 degrees Celsius, if you want to raise the temperature from 25 to 26, how much temperature is raised, ma? How many degrees of temperature is raised? 1 degree. To increase the temperature by 1 degree, how much heat energy is required? How much heat energy is required? To increase the temperature of 1 gram, to increase the temperature of 1 gram of lithium by 1 degree Celsius, how much energy is required? How much heat is required? Is called what? Specific heat. Specific heat means what? The heat required in calories. The heat required in calories for 1 gram of lithium to increase its temperature by how many degrees? 1 degree. To increase the temperature by 1 degree, how much temperature is required is called what? Now, how much heat energy is required is called what? Specific heat. Okay, that means what now? If you want to increase the temperature of 1 gram of lithium by 1 degree, how many calories energy required? Heat energy 0.941 calories energy is required. That one keep in mind. And also remember 1 calorie is equal to 4.2 joules. 4.18 means 4.2 joules. Okay, so in joules or calories we can take here. Next, now which one has more specific heat here? Lithium has more specific heat and cesium has very less specific heat. Next, conduction power. Conduction power means good conductor or bad conductor of electricity. That is called conduction power. So all are good conductors of heat and electricity. All means what? Now you have all first year group elements. Lithium, sodium, potassium, rubidium, cesium, all are good conductors of heat and electricity because of loosely held valence electron. Loosely held valence electron. What is the outermost electronic configuration? NS1. NS1 means one electron will be present in s orbitals. Okay, ns orbital contains one electron. So this one electron is unpaired electron, and this electron is loosely held by the nucleus. This electron is responsible for the electrical conductivity and heat conductivity, thermal conductivity and electrical conductivity. So next important area is that standard oxidation potential and standard reduction potential. Standard oxidation potential, standard reduction potential. So here SOP, SOP stands for what, ma? Standard oxidation potential. Standard oxidation potential is SOP. What is SRP meaning here? SRP stands for what? Standard reduction potential. Standard reduction potential, standard oxidation potential. So now here SOP values will be high for alkali metals. Standard oxidation potentials will be high for alkali metals because they undergo oxidation. Suppose you take sodium. Sodium easily loses one electron. Sodium loses one electron to become Na plus ion. So here sodium atom is ready to lose one electron. Here loss of electron is called what? Oxidation. Loss of electron is called what? Oxidation. So sodium can undergo oxidation easily. Sodium can undergo oxidation easily. That means its oxidizing potential is more. Sodium oxidizing potential is more because it easily undergoes oxidation. That's why standard oxidation potential is high for alkali metals because they undergo oxidation easily. And reduction potential, SRP means standard reduction potential values will be very less. Standard reduction potentials will be very less. Why? They cannot undergo reduction. These alkali metals cannot undergo reduction. Reduction meaning what? Gain of electrons. They cannot gain electrons, but they will lose electrons. They undergo oxidation easily by losing electrons. That's why they have more SOP values and very less SRP values. So they have what now here? More SOP values, more SOP values and less and very less SRP values. SRP stands for what here? Standard reduction potential. SOP stands for standard oxidation potential. This point keep in mind. Again, if you take now lithium, sodium, potassium up to cesium, which is most metallic, which will lose electron easily? Cesium. So cesium is most electropositive, right? Most electropositive meaning what? It loses electron very easily. When it loses electron very easily, what happens now? When it loses electron very easily, it is undergoing oxidation easily. Cesium undergoes oxidation easily. When cesium undergoes oxidation easily, it has more oxidation potential than what? Even sodium. That means what now? From top to bottom, SOP value is increasing. From top to bottom, metallic nature increasing, meaning what? SOP value increasing. SOP values are increasing. Next, since alkali metals easily lose NS1 electron, the outermost electron is then a valence electron, they can lose easily ns1 electron, and thus they have high values of what oxidation potential. So more SOP values will be there for alkali metals, because alkali metal loses electron easily, so undergoes oxidation easily and have higher values of oxidation potential. Next, second point about this, what standard oxidation potential means SOP. SOP. The standard oxidation potentials of alkali metals in volts are what listed below. See, lithium has what plus 3.05, sodium has what plus 2.71, potassium has what plus 2.93 volt, and rubidium has what plus 2.99, and cesium has what plus 2.99. So rubidium is equal to what? Cesium. And potassium has less than what? Rubidium. Sodium has less than this one. But highest is for what now here? Lithium. Lithium has highest. Actually, lithium has small size. Lithium has what? Small size. But it should have lesser value of SOP generally. But in aqueous solution, in water, in the aqueous solution, that is in water, lithium has what? More oxidation potential. The highest oxidation potential is more is for what? Lithium. It is exceptional thing we have to remember here. Exceptionally, lithium has what? Highest SOP value. So it is what now here? Highest SOP. SOP means standard oxidation potential. So standard oxidation potential value is highest for lithium in aqueous solution. That point we have to keep in mind. Remaining cases, sodium to potassium increasing, potassium to rubidium increasing. Rubidium SOP value is nearly equal to cesium. So like this, we have to understand concept here. So in lithium has anomalous behavior. The first element of the group, that is lithium, it exhibits what? It shows what? Anomalous behavior. Anomalous behavior means different behavior from the other elements. So lithium exceptionally has more SOP value. That point we have to keep in mind. Next, more is oxidation potential. More is the tendency to get oxidized. If oxidation potential is more, what does it mean? That element undergoes oxidation very easily, and thus more powerful is reducing nature. More powerful is reducing nature in aqueous medium. That means what here? If anything undergoes oxidation easily, if anything undergoes oxidation easily, it will act as powerful reducing agent. So here lithium has what now? Highest SOP. Highest SOP. Therefore, what we have to understand here, easily undergoes oxidation. Easily undergoes oxidation. Easily oxidizes. Easily oxidizes. Means easily oxidizes means what? Easily loses electron. Easily loses electron. When it loses electron easily, it will act as what? Powerful oxidizing agent, reducing agent. As easily it is undergoing oxidation. If anything undergoes oxidation very easily, it will act as powerful reducing agent. Powerful reducing agent. Therefore, lithium is what now here? Lithium is what? Powerful reducing agent. So why lithium is a powerful reducing agent here? Lithium is powerful reducing agent. Reducing agent. Why it is powerful reducing agent? Since it undergoes oxidation easily. Since it undergoes oxidation easily. It undergoes oxidation easily, very easily. Undergoing oxidation meaning what? Losing electron. It will lose electron easily. Whichever undergoes oxidation easily will act as powerful reducing agent. So among all the alkali metals, which is strongest reducing agent? Lithium. Strongest reducing agent is what ma? Lithium. So among the alkali metals, strongest means powerful reducing agent. Reducing agent is what? Lithium. In what? Aqueous form. In aqueous solution. In aqueous solution means in water. In aqueous solution, which will be powerful reducing agent, which is strongest reducing agent? Lithium. Remember that point. Okay. If it is not water, if it is not aqueous solution, then cesium will be powerful reducing agent. Then cesium will be powerful reducing agent. So this point please keep in mind. Lithium undergoes oxidation easily, therefore strongest reducing agent. That is why alkali metals liberate means release H2 gas from H2O and HCl. They can release H2 gas from water and HCl. Okay, because of powerful reducing nature. Because of powerful reducing nature. Now you check it here. Here 2 H2O is there now. In every H2O there will be H plus and OH minus now. In every H2O there will be one H plus, one OH minus. How many molecules we have taken here? 2. That's why there will be 2 H plus ions, 2 OH minus ions. 2 H plus ions will be there, 2 OH minus ions will be there. In what? H2O. So in every water molecule, 1 H plus, 1 OH minus, we know. In 2 H2O molecules, 2 H plus, 2 OH minus. Now this metal will take what? OH minus. Metal will take OH minus. 2 metals will take 2 OH minus. So 2 MOH. M plus cation, OH minus anion. And the 2 H plus ions will be released, will be liberated, will be released as what? H2 gas. So H2 gas will be released from water. So the alkali metal is reducing what? Is what here? Releasing what? H2 gas. Next, here 2 HCl. In 1 HCl, 1 H plus there. In 2 HCl, 2 H plus there. And 2 Cl minus there. 2 H plus ions, 2 Cl minus ions. Now here 2 metal atoms will take 2 Cl minus to form 2 MCl. Like NaCl, MCl will form M plus 1 cation, Cl minus 1 anion. The remaining 2 H plus ions will be released as what? H2 gas. That means the alkali metals acting as which agents here? Reducing agents. Reducing agents. The alkali metals acting as reducing agents, they will reduce the HCl into water, H2. These alkali metals will reduce HCl to H2. And the alkali metals will reduce the water, will reduce the H2O to what? H2 gas. Like this, removal of hydrogen is called what? Reduction. Removal of hydrogen is called reduction. This reduction is by the help of what? Alkali metal. The reduction means removal of hydrogen. This reduction is due to what? Alkali metal. So alkali metals are responsible for reduction. That's the which agents they are? Reducing agents. Reducing agents. Is the point clear to all? So what is main thing to understand here? Alkali metals undergo oxidation. Therefore, they are reducing agents. Got it? Next. Okay. So next condition is that, however, an examination of ionization energies. If you observe the ionization energy, examination of ionization energies, okay, of alkali metals, reveal that the examination reveals that lithium should have the minimum tendency to lose electron. Generally, lithium is having what? Small size, na? Lithium is having small size. Lithium smaller sized and cesium has large size. So from the concept of ionization energy, a small size has high ionization energy, higher ionization energy, and cesium has lower ionization energy. Then here low IP value means what? It should lose the electron easily. It should undergo oxidation easily. But actually what is happening? The lithium is able to lose electron easily, we are saying. It is undergoing oxidation easily, though it is having high ionization energy. Okay, that concept we have to see. And thus, its reducing nature should be minimum. The lithium reducing nature should be generally minimum. Because of high IP value, it should undergo oxidation with difficulty, and reducing nature should be less according to theory. But here, the greatest reducing nature of lithium in aqueous medium, in aqueous solution, in water, is accounted due to the maximum hydration energy of lithium. Maximum hydration energy of lithium ion. The lithium ion is the smallest cation here in the first group. In the group 1, lithium ion is smallest cation. Smaller the cation, more hydration energy. Smaller the cation, more hydration energy. Because of greater hydration energy, the lithium will lose one electron easily. So lithium loses one electron easily to form Li plus aqueous, Li plus aqueous, due to what now here? More hydration energy. More hydration energy of lithium. This is called hydration enthalpy also. Hydration enthalpy is greater for lithium. Because of more hydration enthalpy, the lithium is able to lose electron easily. That means lithium undergoes oxidation easily. When lithium undergoes oxidation easily in water, it will act as strongest reducing agent. The reason we have to understand. Okay, so here lithium has high ionization energy. It has higher ionization energy, and also what? High hydration enthalpy. Hydration enthalpy. Because of high hydration enthalpy, it is ready to lose one electron, undergo oxidation very easily. That point keep in mind. So here, first lithium solid will change into lithium gas. Solid to gas is called what? Sublimation. Solid to gas is called directly sublimation. So here delta H1 means heat of sublimation. A delta H1 we are taking as enthalpy change. Enthalpy change 1. Delta H1 we are taking as what? Heat of sublimation or enthalpy of sublimation. This is given by delta H sublimation. Delta H sublimation. Next one, lithium gaseous atom. Lithium gaseous atom is going to lithium gaseous ion. Atom is going to ion. Neutral lithium gaseous atom is going to lithium unipositive ion. So it is what the energy required is what now here? Ionization energy. The energy required by the atom to lose one electron is called ionization energy. It is ionization energy. Here, the energy required by lithium solid to convert into gas is called what? Sublimation enthalpy. What is called? Sublimation energy. Sublimation energy or sublimation enthalpy. Here, ionization enthalpy is required here to convert the lithium gaseous atom into lithium gaseous ion. Now, here, electron is released here. Now, this second enthalpy is taken as what? Ionization enthalpy. The second enthalpy in this equation is equal to what? First ionization enthalpy. Why it is called first ionization enthalpy? We are removing electron from neutral atom now. The energy required to remove electron from neutral atom is called first ionization enthalpy. First ionization enthalpy. Next, Li plus gaseous ion is interacting with water, H2O, is surrounded by water. When Li plus gaseous ion is surrounded by water molecules in aqueous medium, what happens? Some amount of energy will be released. That energy released is called hydration enthalpy. So in this concept now here, energy will be released. Remember, energy will be released. This is called hydration enthalpy. This energy released is called what now? Hydration energy or hydration enthalpy. So hydration enthalpy meaning what, ma? Whenever gaseous lithium ion, metal ion, is surrounded by water molecules, due to attractions between the water and Li plus, some amount of energy will be released. This is called hydration energy. Okay. If this cation size is lesser, more hydration energy will be released. So this enthalpy, third enthalpy change is taken as what? Heat of hydration or heat of enthalpy of hydration. So delta H hydration. Delta H hydration we say. So enthalpy of hydration is negative here. Why it is negative? The energy is released or absorbed here. The energy is released. The energy is released indicating what? Negative value. Delta H will be negative. Enthalpy change will be negative. But here energy absorbed, here also energy absorbed. That's why we have taken plus delta Hs. A plus ionization energy. Okay. Now here, directly if lithium solid is converting into lithium aqueous. Here lithium solid to lithium aqueous means how many steps are there here? First solid will change into gas. Again gas will change into ion, gaseous ion. This gaseous ion will change into aqueous ion, So this solid to lithium aqueous will involve 3 steps. When you dissolve this lithium solid in water, it will convert into Li plus aqueous along with some electron here. Energy, one electron is released here. Okay. Next one here, this total delta H now, the total enthalpy change, the total energy change is equal to delta H1 value plus delta H2 in second step, delta H3 in third step. The sum of all the three enthalpy changes will be equal to total enthalpy change here. Okay, so what is delta H1 here? Enthalpy of sublimation. What is delta H2 here? Ionization enthalpy, ionization energy. What is delta H3 here? Hydration enthalpy. HYD means hydration enthalpy. Hydration enthalpy. So here it is positive value. It is also positive value, but it is negative value because energy released here. So it is negative value. So this is what we have to understand concept. Similarly, sodium. Sodium solid is dissolved in water in aqueous medium is going to sodium aqueous. Sodium aqueous. Here also solid to aqueous. Solid to aqueous, how many steps? 3 steps. Okay. So again here the total enthalpy change, delta H total is equal to delta H sublimation plus ionization enthalpy minus delta H hydration enthalpy. The same in case of lithium and sodium. Next, hydration enthalpy. Delta H hydration means hydration energy for lithium is greater than hydration enthalpy of sodium. Hydration enthalpy of lithium is greater than hydration enthalpy of sodium. Why? Lithium small size, sodium large size. If small size cation is there, more hydration enthalpy. Therefore, large negative delta H values are observed in case of lithium. That means in case of lithium, hydration enthalpy is more, meaning what? When lithium interacts with water, more energy is released here. More hydration energy is released. That's why more negative hydration enthalpy. More negative hydration enthalpy we have to say. The hydration enthalpy is more negative because more amount of heat energy is released here in case of lithium. But when sodium interacts with water, when sodium undergoes hydration, here also energy will be released here. Here also some amount of energy will be released, but less amount of energy is released here. Less amount of energy is released here. So less hydration enthalpy. That's why less negative. Less negative means less amount of energy released. Here more negative meaning what? More amount of energy is released. Okay, so that's what we have to understand concept. Okay, no? So it's about what now here, and this concept explains what now for more possibility of lithium to get itself oxidized. So lithium undergoes oxidation easily or have more reducing nature. So lithium undergoes oxidation easily, therefore acts as powerful reducing agent. Powerful reducing agent. Next. So characteristic flame colors. This is important concept now. So the flame colors concept is important. Flame colors. So characteristic flame colors. The alkali metals, first year group metals and their salts. Alkali metals and their salts give characteristic color, specific color to Bunsen flame. To the Bunsen flame, they will give specific color. Each cation will give specific color. That is called flame coloration. Flame coloration. The flame energy causes, the energy of the flame will cause excitation of the outermost electrons, causes an excitation of the outermost electron, which on reverting back to its ground state, its initial position, the electron absorbs energy from flame. The electron, valence electron of sodium, suppose the valence electron of sodium, suppose you take here one some flame here, some flame you take here. So now we introduce what now here, NaS here. Okay, in this NaSl electron is there now, valence electron is there now. That valence electron will absorb this energy. This energy will be absorbed and electron will go to excited state. Electron will go to excited state. This with star symbol it is called what? Excited electron. This excited electron again will come back to ground state now. Excited electron again will come back to ground state. When electron is coming back to ground state, it will release some amount of energy. This energy will be in the form of color, a particular color, radiation. This is called flame color. When electron is excited and again de-excited, some amount of energy will be released in the form of a specific color. This is called flame color. Flame color. Okay, ma? So, and initial position, the electron is coming back to initial position and gives out the absorbed energy. How much energy absorbed here, that much amount of energy will be released. Suppose if X joules energy absorbed by electron for excitation, the same X joules energy will be released when it is undergoing de-excitation. When electron is coming back to the ground state, it will emit same amount of energy. As what? In the form of what? Visible light. In the form of a visible light. Visible light contains how many colors? 7 colors. V, I, B, G, Y, O, R. VIBGR. VIBGR colors. 7 colors will be present in visible light. In the form of any one color, the flame color will be there. These colors differ from each other. Okay, from one element to other element, this color exhibited will be different. Suppose lithium will be giving which color? Crimson red. Which color? Crimson red color. Thick red color. So crimson red color will be given by lithium salts. The lithium salts will give which flame color? Crimson red. The flame color of lithium salts will be crimson red. And the flame color of sodium will be golden yellow. When you introduce the sodium salt into the flame, Bunsen flame, we get what now here? We get the golden yellow color. The golden yellow colored flame will be obtained when sodium is introduced into flame. Okay, next. Potassium flame color is what? Pale violet. Pale means light color. Pale meaning what? Light. So pale violet, light violet color from potassium salts. And rubidium salts will give red violet. Pale violet, potassium. Red violet, rubidium. And what is the flame color of cesium here? Blue violet. The bluish violet. The bluish violet will be given by cesium. That means what? In VIBGR, the violet and blue will be mixed. The combination of violet and blue will be giving blue violet. Blue violet. Okay, so these flame colors we have to remember. And these different colors are due to different ionization energies of alkali metals. The energy released is minimum in the case of Li plus and increases what? In the order. Okay, so now here the energy here red is there now here in a VIBGR now. If you take V, I, B, G, Y, O, R, VIBGR. In VIBGR 7 colors, which will be least energy here? Red color is least energy. Least energy by red color. Least energy meaning what? Longest wavelength. Red has longest wavelength and least energy. Now lithium, from lithium salt, whatever the light is coming is what now? Red. The crimson red means red only. The red color is coming from lithium salt. Na? The flame color of lithium is what? Red. This red is having least energy. Na? That means what you have to understand now here, that lithium has more ionization energy. Lithium small size, na? That's why more ionization energy, but the energy released will be minimum. The energy released from lithium is minimum. When energy is minimum, which color will be there in visible light? Red color should be given. And now see here, cesium, you see, cesium is having what? Blue violet. Now violet color is what? Most energetic. Most energetic color. Most energy is for what now? Violet. Violet is having more energy in the VIBGR. Okay, that means what now? When you take the cesium, when you introduce cesium into flame, we get violet color. Means more energy. The violet color with more energy will be released from cesium. But from lithium, we get red color with less energy. Now here, the energy released will be least for lithium. The energy released from lithium will be least. And cesium, from cesium salts, more energy will be released. Whenever energy is less, lambda will be more, na? According to Planck's equation, we know E is equal to, energy is equal to H nu. H nu means Hc by lambda. Hc by lambda. Now lambda and energy, how these two related here? Inversely. When lambda is less, energy will be more. When energy is less, lambda will be more. Now here, what I am saying here, energy released from lithium is least, na? The energy flame, energy released from lithium is for less. When energy is less for lithium, now the lithium will be having more wavelength now here. The flame color of lithium will be having more wavelength because energy is less, na? Whenever energy is less for lithium flame color, the lithium flame color will be having more wavelength. Inversely proportional, energy and wavelength. And frequency also directly proportional energy. Frequency, this one new. Frequency and energy, how they are related directly. So when energy is greater, frequency also will be greater. That's why here, cesium more energy, cesium more frequency. From cesium salt, whatever the flame color is coming, that flame color will have more frequency, more energy, but less wavelength. Is that clear, ma? So the flame color of cesium, the flame color of cesium has what? More frequency, more energy, more frequency and more energy, but less wavelength, less wavelength. The shortest wavelength will be there, but more frequency and more energy will be released. Is that clear, ma? So it's about flame coloration. Flame coloration. So these elements are collectively called alkali metals. First A group elements are what now? Group 1 elements are called alkali metals. And group 1 is called alkali group. Alkali group. As why it is called so? The hydroxides of these metals are soluble in water. And these solutions are highly alkaline in nature. Alkaline meaning what? Basic in nature. That's why alkali metals. And alkali metals are highly reactive and hence do not occur in free state, but are widely distributed in the nature in form of combined state. In combined state, they will be available in the nature. In the form of what? Halide salts, in the form of oxides of alkali metals, in the form of silicates of alkali metals, in the form of borates of alkali metals, and in the form of nitrates of alkali metals. They will be available in the nature. Of all the alkali metals, only sodium and potassium are found in abundance, means large quantities. In large quantities, what will be available in the nature? Sodium and potassium. That is, they are